we can actually correct it then within. Yeah, no, you can go ahead with questions. Yeah.
Shall I start? Okay. So good afternoon. So I am going to discuss the interface between particle physics and cosmology. So this is the title of my talk, New Physics with an Effective in the CMB. So this talk based on these two papers. So the main idea of this talk, if we have a BSM interaction between standard model fermion and BSM mediators, so then the BSM mediator face different type of constant from laboratory experiment, astrophysical and cosmological observation. So our objective is to identify the region of parameter space where the cosmological observation put a strong stringent constant. So this is a cartoon figure in the plane of the mass of the BSM mediator and the coupling. So this red line is our point of interest. So this red line corresponds to the ineffective upper bound from Planck, and the region of the left side of this line are excluded from the Planck observation. Okay, so let me start with some brief discussion about Neutrino cosmology. So around BBN, just after electron positron annihilation, so neutrino are the second abundant particle in the early universe, and those neutrino associated with the relativistic degrees of freedom, they are associated with this parameter called an effective, and it is parameterized as the ratio between the neutrino density and the photon density, and it's play a crucial role describing the dynamics of the thermal history of the universe. And the Planck observation precisely measured the ineffective value at the times of CMB, so assuming lambda CDM cosmology. So there is an independent constant from the BBN, although I am not going to focus on BBN constant. Okay, so let's start the standard model contribution to the ineffective. So this is the effective interaction associated with the neutrino and the electron and positron. So let's assume the early universe temperature around 10 MeV, where neutrino and photon share the same temperature. As temperature falls, so looks the backward direction. As temperature falls, universe expand, the weak interaction fall faster than the electromagnetic interaction. So as a result, neutrino are decoupled from the photon one. Okay, so the temperature below electron mass, electron positron annihilate to the photon. So that means the entire energy of electron positron transform to the photon bar. So therefore, the temperature increase in the photon bar compared to the neutrino. So as you can see from the rise behavior. If you go further the lower temperature, this ratio becomes saturated, and once you know the ratio, then you can find out what is the ineffective value using this simple expression. Okay, so within the standard model, it turns out that ineffective at CMB 3.043. So therefore, we have Planck observation on ineffective and standard model contribution on the ineffective. It shows that there is additional contribution to the ineffectives that's around 0.28, and that indicate the scope of new physics. So there are different ways people have addressed this additional ineffective contribution. So one of the possible way that we are interested, that is introducing non-standard neutrino interaction with the light gauge volume. So before us, so this is L mu, these are the two popular scenario, V minus L, L mu minus L tau. People have addressed this type of, so they have addressed in this context. So what we have done, so instead of specific gauge extended model, we consider generic U1X model with arbitrary charge assignment. And as you know, the specific anomaly free charge assignment gives rise to different type of gauge reaction in this scenario. I'm just coming to that. Okay. So the presence of Z prime. So this is the interaction, very simple interaction that relevant for our analysis. And these are the parameter: light graduation, mass, coupling, and the lepton charge assignment of x1, x2, x3. Those are associated with the first, second, third generation of the leptons. So the Z prime here form a different path, and Z prime act as a bridge between the neutrino sector and the photon sector, and also balance the energy density between these two sectors via scattering and the decay. So the major task here to find out to study the temperature evolution for each sector. So those for that you need to solve this complicated Boltzmann equation. Okay, so in order to understand how the arbitrary charge assignment can significantly impact the N effective, so here we show the variation of N effective with the thermal bath temperature with different value of x1, x2, x3. So just focus this x1 charge. So that's the charge assignment for the first generation of the lepton. So with increase of the x1 charge, the N effective value, N effective is increases. So this is the lower one for x1 equal to 0, for the middle one for x1 equal to 1, mod of x1 equal to 1, and the red one is mod of x1 equal to 3. So that is because the it's enhanced the effective coupling, and that leading to the enhance in the contribution in the N effective. Okay, so this is the plot here. You can see the variation of N effective with the gauge coupling. So let's, for the case of x1 not equal to 0, that is the blue and the green line. So with increase of this the coupling, the N effective value increases. So that is because the non-standard interaction enhance. But for the case of x1 equal to 0, it shows something peculiar behavior. So that is because for x1 equal to 0, Z prime doesn't have the T level interaction with the E plus E minus. It interact via the induced coupling. Okay, so then depending on x1 charge, one can classify all U1X model with the two categories. In the category 1, where Z prime has T level interaction with the electron positron. So these are the U1 extended model fall in this category. And in the second category, where Z prime doesn't have T level interaction, they interact via induced coupling. So these are the U1 extended model fall that category. Okay, so we have considered these are the all U1 extended scenario. We have considered the green color highlighted models are correspond to x1 not equal to 0. So others x1 equal to 0. Okay, so this is the important plot. So let me discuss. So this is the variation of N effective with the Z prime mass. So as you can see, with the increase of the Z prime mass, the BSM contribution to N effective decreases. So that is because Z prime density suppressed with increase of the Z prime mass. So and you can also see, so there is a three different distinct type of behavior in the plane of N effective and MZ prime. So those are corresponds to. So if you look into this lower one, so this lower one corresponds to the U1X model where x1 equal to 0. So these are the U1X scenario. The middle one corresponds to mod of x1 equal to 1, and the top one is corresponds to mod of x1 equal to 3. And as I mentioned earlier, so for a fixed Z prime, if you increase the x1 value, the N effective value increases. So it is clear from this plot. Okay, so these are the some exclusion plot from NFT. So here we constant where we show the constant from NFT and also the laboratory experiment in the plane of the light jet prime mass and the coupling with the U1x model with x1 not equal to 0. So this red dot line is our point of interest. So this is the upper bound on NFT from Planck. So the red shaded area are excluded by the Planck, and along with we show the different laboratory experiment constant just compared to the our bound. And as you can see, there are some region, specifically lower region and in between region. So the NFT put a more severe constant compared to the others. So this is the case for B minus 3 LE. So the difference between these two plots is that the red contour, red dash line contour shifted towards the higher mass region because of the x1 charge or effective charge x1. So effective charge now it's enhanced because effective charge is x1 times gx. So it's shifted towards the right. And accordingly, the other constant also modified because of your U1x charge assignment are different from the others. So if you look into from V minus L to LE minus LE mu, but the red dot line, the contour line, almost similar, except from the experimental bound. Okay, so this is the case for U1x model with x1 equal to 0. So that means Z prime doesn't have T-level interaction with the electron positron. So if we neglect the induced coupling, as I mentioned, Z prime can connect it to electron positron via induced coupling. So then this is the the 2 sigma upper limit on N effective, and it's almost independent of GS because the energy density of Z prime 100% converted to the neutrino sector only. So if you allow the non-zero epsilon, so then it looks like this. So in this region, there is a basically competition between scattering and the decay. Okay. So similarly for the other cases. So with this, I would like to summarize the new interaction of Z prime with electron positron and neutrino that can potentially impact the neutrino decoupling and hence the N effective value. And as I mentioned, for each model, each U1 extended scenario, you can find out there is some region where the N effective bound is more stringent constant compared to the others. And these U1 extended models are widely used in particle physics and also cosmology. We hope the bound derived by us from N effective relevant for the community. So with this, I would like to stop. Thank you.
Question, please. Yes.
Very basic question. So you I think explained it, but I missed it. So when you have a light Z prime,
Yeah.
The bound is violated, ineffective.
Yeah.
Can you say again why you get this 10 MeV scale? From where does that come? Is that from BBN or are we looking at only CMB?
CMB.
So then why the 10 MeV around that? Why that scale?
Okay, as you can see, so this is the upper bound. It is around 3.33.
Yeah.
So if you go along, the N effective decreases towards the standard model. So if you go towards left, N effective increases. So it's depend on mass. So that's why this is the upper bound.
No, but why 10 MeV scale? Where is that coming from?
Why 10 MeV? So I'm saying, so if you if you take that let's say 15 MeV, so then your N effective value is less than let's say 3 point something. Now, if you consider what, so this phenomena, as I mentioned, this phenomena happen around the MeV scale. Neutrino decoupling happen around 2 to 3 MeV. So if you consider, let's say 1 GeV, so then you don't have that much number density.
Is that the neutrino
Yes,
decoupling scale?
yes.
That's around 10 MeV.
Yeah.
Yeah, that's all I was.
No.
No.
I'm not saying neutrino decoupling scale is around 2 to 3 MeV.
So it should be, that is what is setting that scale or what? The neutrino decoupling.
Okay. So as I said, if you consider Z equal to 1 GeV, so the number density is suppressed. So then it doesn't affect the neutrino decoupling. So neutrino decoupling is here.
Okay,
Can talk
anybody
later.
else?
Sorry. So,
I don't see any other hands up. So let me request Rahul Sinha to present the talk. Thank you. So Rahul Sinha will be talking on his title is the CP violation observed in decays, a signal of new physics.
Oh, you put it on this. That's correct, right? Hey, it's great to be back home. I thank the organizers and my friends for having me over for this momentous occasion where we are celebrating Rajaji's contribution. So I must say that my whole last 30 years, I feel I had a satisfying career, and part of it is Rajaji and RR, another who were interested in getting me here. And that played a major role. And so let me begin by talking about one of the hot topics, which has been whether CP violation that's observed in D decays is a signal of new physics. This work is done with my collaborators and should be submitted soon. It's been highly delayed, so I thought it apt to report it at this meeting. Earlier, I was supposed to be here in February, and I was going to present that. But then it got a little bit more refined and things. Now, actually, LHC-B on 14 November 2011 reported what was called the first evidence of CP violation in D decays. And the result was just about a little more than 3 sigma. And we had a meeting here in December of that year. Kibble was there, Fritsch was there, and but this was not a topic of discussion. However, I do remember that this was being hotly debated at that time, whether it's indeed a signal of new physics or not. Okay, and that argument continued, and even after the signal became 5 sigma in 2019, Morion, they reported it. The argument remained whether it's a signature of new physics or not. Now, then last year, I mean, almost 2 years back, sorry, when I got interested in it was when they had measured the direct asymmetry in KK and pi pi. Now, earlier Ballard, of course, got the measurement of this pi pi mode. I forgot the citation, but this is an upper limit. And the branching ratios for this have already been known for a long time in PDG. So, given that information, we start with the thing. So, when I was a student, it was said, well, deep physics, there is nothing new. If you see anything new by chance, it's going to be new physics. So, we started doing deep physics 40 years back, and D2 pi pi was D2 pi pi and D2 KK were one of the first papers I wrote in D decays. Okay, we had the isospin relations and all that. And it was, the evidence for CP violation DT to KP has raised a debate now, again, whether it's new physics or not. So all those dogmas that we were told that, no, this is small in D decay, this is big, everything turns out to be wrong. When CP violation was regarded as a signature of new physics, now again is being debated whether it's indeed a signature of new physics or not. And that is because we have such little control on non-perturbative effects that go on in light decays. Now, not everything, of course, is doubted, but the confusion stems from the difficulty in reliably estimating long-distance contributions, that is rescattering effects, as well as establishing that the penguin contribution is too large to be accepted in this standard model. Okay. So we know that there is a large CP asymmetry. That means that obviously there's a tree and a penguin interfering. And if the penguin is not there, then of course you would not find CP violation. That is why we were told that 40 years back that no, CP violation is not needed. You don't take penguins in your decay. And of course, it was reasonable because in those days, even penguin in top decay, B decays were not regarded as very important because top was light. Okay. And B had been established, so people didn't think penguins were very small. So several, almost more than 200 papers have examined this issue. And after all that, there is no clear evidence. There are people who say, well, rescattering is the reason why this is happening. On the other hand, some people say, well, such a large asymmetry is really doubtful in B decays, but there's no clear answer which cannot be refuted. Okay, so our approach differs from the others in the sense that we estimate penguins directly from experimental data. We don't use any model to extract penguins, and so therefore there is no doubt when we say that penguins are this big. And then what we do is we don't take a model for final state interactions. We actually use only unitarity. Okay, and it turns out that's enough. So that is now so the way these D decays were treated is to have sort of topological amplitudes. Tree diagram where this meson comes outside, they say color suppressed tree because of color rearrangements here. And we were told that these are the only two diagrams 40 years back which can contribute. The rest is nonsense. You do not take them. Okay. Now today, the whole scenario has changed. We take everything. Even in B decays, we worry about things. So we are told, well, this is too light a quark, chiral suppression, soft gluons, nothing. All concepts were completely different. Anyway, the more important thing is that these are all identical, W vertex. Okay. Here there is loop diagrams. And they were genuinely believed to be suppressed. Nobody could argue. In our papers, we argued taking the exchange diagrams and corresponding diagrams in other decays. But penguins, even we believed, were too tiny. And in the penguins, what happens is that there is a DS or a B quark that runs in this blue line everywhere. And if CP violation is seen, then obviously there is a new phase there. And you must have two different weak phases to see CP violation and two different strong phases. So that is a must. Okay. So what you do is you look at the amplitudes for these in terms of for the D to pi pi modes, pi plus pi minus, pi 0, and D plus to pi plus pi 0 in terms of these topological amplitudes. And these lambda Ds are the CKM factors that appear in the decay. Okay. And the point is that you can use unitarity because as Jim pointed out in the morning, there is unitarity and we can use unitarity to eliminate lambda B in favor of lambda D and lambda S. Different people use different parameterization. Some people will eliminate lambda S, some will eliminate lambda D, but there's a reparameterization invariance. All your physics results should be the same. Okay. Now the point is, what is an interesting choice? Okay. People take, obviously some people feel, oh, B quark, because keep the B quark, eliminate the S quark. We choose to do this. I'll explain why. And when you do that, these amplitudes, you eliminate that and then recombine these amplitudes such that, you can define T as the magnitude of this times this amplitude. And this gives you a short form notation of T plus some weak phase that comes with the penguin diagram relative. So all weak phase is relative, strong phase is relative. I've absorbed the strong phases inside the P relative strong phase. And so basically that's it. The weak phase is here for pi naught, pi naught. This is the way it appears. And this gives you, as you can see, if I take a plus minus by root 2, then a plus minus by root 2 plus a naught naught is equal to a plus naught. And that gives you this beautiful isospin relation, which we have written here. Okay. This isospin relation is well known. We have used it. And geometrically, it is represented by a plus minus by root 2 plus a naught naught is a plus naught. So, and for the conjugate mode, the same thing happens. If you're going to see CP violation, then the conjugate mode is actually to be seen. If there's no CP violation, the two triangles will just overlap. Okay. Now, what happened was when we were doing, we derived the first bound for pi naught in V decays. And we realized that doing a coordinate system here is a wonderful way to do things, because I can solve for things using experimental data without things. So we defined this coordinate system, and I followed with the same coordinate system here. There is this base which is x1, y1, x2, y2, and then L0 and minus L0 on this. And the isospin amplitudes are here. So the interesting thing that happens is that, these were the amplitudes I had written earlier for the a plus minus, a naught naught and this. And I can have t plus p e to the power minus I phi, e to the power I phi angle, and then I get the a plus naught, the blue one. If I have for the conjugate mode, the weak phase switches, so I have the minus I phi. So this is how it will be done. All I do is I dissect this point at the origin, I make a perpendicular to that line, and I have this weak phase here and the penguin. And the smaller I make the weak phase, the larger the size of the penguin, because, right? So if I want to see really large penguins, then I must go for a small phi. And I must go for the most accurate phi measurement, because if I can do that, then I have a better handle. Okay. So that's what, over years of experience, I realized that that's what the game is. I'm going to skip the next sheet. Oh, sorry. I'm going to skip this. If I have time, I'll come to it later, but I don't think I'll have time, because not only can we get the amplitudes, we'll also get these isospins things and other information. The information is there. Now, in the morning, you had seen the Wolfenstein parameterization for this. Now, in DD case, we were told no CP violation. Why were we told no CP violation? Because first of all, at lambda 4th order, there is nothing. So you have to keep at least lambda 5 to be able to see CP violation in this decay. Sorry, I always fat fingers. Yeah. So the lambda 5 order is kept, and then you can generate a phase for lambda d, which is so tiny. And see how accurately I know these things. What people do is they will eliminate one of the phase, keep lambda b, which is not so well known, right? It is not as accurately known. And then obviously they will get bigger error in P and not be able to distinguish whether it's new physics or not. So we were aware of this, we use this and lambda s. So what happens is that the weak phase phi that I had talked about is just simply so tiny with an error that is actually just the last. So well the phi is known. With this phi is the smallest weak phase in this and the most accurately known. So when I have taken the smallest phase, I'm going to get the largest P. Okay. And everything will turn out 10 minutes. So in terms of the coordinates, the observables can be derived simply, the x1, y1, L, I have the observables and I can derive them. And in terms of the things, so observables, I've inverted it, got all the coordinate system. So I know exactly, if I know the data, I know the distribution, I know where the coordinates spread. And so what I do is we work in this complex coordinate system and extract all the observables that you can, all the topological amplitudes, the isospin amplitudes, and other related things like T0 here, which gives information. So everything is extracted. And when I extract that, just to show you that this is central value, look at how much the P overlap, the two triangles are overlapping. So that's how small a CP violation has been measured. Okay. Is that small And even that is giving evidence. It's not, so there are only central values that I've shown here. And what we are doing is we are only showing two triangles which have this smaller penguin shown. If it's a very big penguin, it's much bigger than the tree. Okay. So that we look at the coordinate system here. It's like 0.21 and here 4. So that's how it looks. Then what we do is we simulate all these observables, 200,000 points. Okay. And we just calculate all the parameters. And this is what happens. Lo and behold, we have the P plus minus, which is the normalized rate with respect to the branching ratio for plus minus. I have done that normalization for a purpose, not for anything, but that is a theoretical estimate that people did. And you can see that a penguin of 0.1 is like, more than, definitely less than 3 sigma. It is more than 3 sigma away from the central value. So these are the values you find. The best fits are like 4 times the branching ratio. A penguin that is 4 times the branching ratio is ridiculous, right? But even here, a value of 0.1 is actually an incredibly large number. Okay. But okay, that's the best because charm loop is running there. Maybe non-perturbative effects, that's what it is. Okay. Now, the other ratio we do is P by T, and you can see that a penguin that is 10%, that see, remember the penguin is a loop. So all those loop factors will come in. Okay. How are you going to enhance it and make it big? So a 0.1, even if you have light quarks, other things going around. In fact, light quarks will give you less of a loop, right? So it's very unlikely that you have this thing, but even a P by T of 0.1 is possible only at 3 sigma deviation. So it shows, data shows that, penguin is a little bit too uncomfortable to handle. And amazingly, a few years back, in 2017, they estimated P plus minus as 0.09 plus minus 0.1. That's close to 10%. Okay. 0.1 value is not, but many people doubted because it's so big. But the point is that they did what is called the light cone sum rule technique. And since the momentum flowing through the penguin loop are order 1 GeV, a perturbative calculation route is regarded reasonable. And then people have given convincing arguments that this is correct. I don't buy any of those arguments rigorously, but yes, 0.1 value would be hard to explain in an honest fashion. Anything bigger than that could be very difficult. And we are finding 40 times bigger than 0.1 as a central value, right? And even a value, even that is like at least 3 sigma away. Okay, if errors go down, things will improve. So the point is that final state interactions, of course, can change the size because we know that final state interactions changes all the amplitudes, everything. So we wanted to examine final state interactions in a model dependent way. So what we do is we do a completely general treatment of final state interactions. It's well known that a two-body scattering of n coupled channels, a convenient parameterization is S matrix. And S matrix is written in terms of a K matrix, which is n by n Hermitian matrix. And we evaluated at MD because this is to be calculated at MD squared, at MD mass. And so what happens is the unitarized amplitude. So what happens is you have a bunch of amplitudes A0, n amplitudes, and they get rescattered through the K matrix to the unitarized amplitudes, which is after rescattering. And since strong interactions conserve isospin, you have to write it for each isospin. Okay. So we will, a penguin has isospin 0 only. Okay. But 3 amplitudes come in there. Both have isospin 0. The T0 amplitude I had is isospin 0, so they can also come in. So the unitary matrix that diagonalizes this thing, let U be a unitary matrix that diagonalizes K with the eigenvalue lambda. And so the unitarized amplitude mod squared is just simply this. I diagonalize the K, make it lambda squared. And so what I prove is that the unitarized amplitude, sum of unitarized amplitude, the probabilities of transition amplitude is smaller than the original amplitude, sum of original amplitude. You can't gain on it. Okay. And to get something big here, you must have at least something big here to start with. So, okay, I can say the unitized amplitude, all of them are 0, one is big, but then I must have enough amplitudes and enough penguin. Okay. And there is one more caveat that comes here, is that the penguins have a weak phase. Therefore, it cannot receive amplitude from a contribution. See, penguins are leading to CP violation. You can't just switch over an amplitude that doesn't have a weak phase to an amplitude that has a weak phase. So you must write this amplitude separately for a penguin diagram. Okay, separately applies to the P amplitudes. And if anomaly of large penguins arises from within the standard model, one must generate large penguin contribution at least one of the channels that rescatters to produce the observed asymmetry. You can't just do it from waving hand or just talking or writing. This has to be obeyed. And most people sort of didn't even realize it. I'm surprised. You know, this is a far cry within standard model because after all, 10% maximum you can generate. So it's impossible, therefore, to rescatter could account for large penguin observation CP asymmetry. Now, the last bit is, if this is an anomaly, then new physics should be able to explain it. But how do you explain such a large asymmetry that's 40 times bigger? Okay, with something that's tiny. New physics can't be big, it's tiny, right? And so the point is, the first problem was that we have ignored electroweak penguins, which is in standard model, a reasonable assumption. You can ignore electroweak penguins, but the moment you add new physics, there can be electroweak penguins. And so we have to include them. Fortunately, the direct asymmetry in this mode is measured, and that means that they can dip the amplitude for A plus minus, and they can differ by as much as this. See, we overlapped the base because there was no direct CP violation, we assumed, because there is no penguin, electroweak penguin. There is no CP violation in the plus minus mode. If electroweak penguin comes, then you can have CP violation. But there can be a maximum difference of this at 1 sigma. This is difference is in fact very small compared to the estimate that we are talking of penguin contribution, right? So even if it shifts, the estimate on penguin won't change. So we did the simulation, checked that out. To a very good approximation, we can assume that P includes the PEW. Okay, small contribution simply because the direct CP asymmetry in the mode is small. If the direct asymmetry in this mode is big, then of course you have violated isospin. Okay, last 2 slides. So we add new physics, parameterize it with n e to the power I phi, and that n e to the power I phi can be rewritten in terms of our weak phase phi as n1, n2, and because what I want to do is only one weak phase. There's one 0 phase and one phi phase. So we recast everything in terms of that. And so what you do is you have n1 and n2, you can solve this out, and then you see that T gets clubbed with n1, P gets clubbed with n2, and so the observable P plus minus that you observe is standard model P plus minus plus I have normalized everything to B plus minus just so that it is compared to what is experimentally done and what we have simulated, and new physics also turns out on the same scale. So the relative strong phase, okay, this is how it is. Then we use experiment. This is obtained from data. We have simulated and obtained. We called it P plus minus in our thing, that's we observed. And P plus minus SM is what is estimated. So we simulate it and get, and then we solve for n plus minus. And when we solve for n plus minus, we find beautiful thing that, so central values is so tiny. So n plus minus of the order 0.0025, much smaller than the estimate of electroweak penguin from theory, okay, is allowing us to obtain new physics. What is happening is just the alignment of these phases. We have such a small phase there, and if you have a phase of new physics, which is like 60 degrees, 30 degrees, then that's enough. Of course, the smaller phase you choose, the bigger the size of new physics, but not very big. It's just in log scale. This is what it is. And, you can explain it within this set. And you need some new physics, yes, but even 10 to the minus 3 is good enough. And so this is, it can explain CP violation. So the last slide is a conclusion. So data indicates that P plus minus is 0.1 is at least 3 sigma away from the estimated values, indicating an unacceptably large penguin diagram, penguin contribution. Okay, reasonable values of n plus minus, smaller than p plus minus, can result in large observed penguin and CP violation. That large observed penguin is essentially, see, the whole thing is that because we are talking of phases, one small phase, another big phase, you have to realign it, and that's what ends up giving you this large numbers. It is not naively it thinks, oh, how is it possible? Such a tiny new physics gives you such a big effect. It does. The central value, if the central values do not change, we would have a clear evidence of new physics. Now, unfortunately, given the history of things, LSEB result, I would be doubtful that it continues. But nevertheless, recently at the August meeting, this year was at ICHAP, right? Yeah, they reported some papers, a different thing of doing analysis, where they were doing the gamma measurements, and there they have to measure the decays, and these modes were included. And so separate analysis with different group was done. And they also found a value little bigger than what I've quoted here. Okay. A much more sophisticated correlations and other things. So I didn't bother including that, but I find it. And if that is indeed the case, then we have new physics. Thank you. Thank you.
For finding.
Well, let's hope it's for the younger people that they should. If there's no view physics, there is no money. This would be basically likely everything is high scale. So people have explained it. There are papers, almost about 50, 60 papers, right from supersymmetric points. They are able to manipulate data and do it. Now, every time there is new LHC constraint, things may get ruled out, but almost a broad variety of physics can explain it. The question is whether direct experimental constraints and this put together are going to come out. So first, the new physics is established, the weak phase is established. Then we have, but right, I mean, there are at least 50 different papers who have gone ahead and done. So the problem I'm having writing a PRL is the citations for them. So we were already exceeding 6 pages. Thank you.
Okay.
Yeah,
So
yes,
just
yes, please.
this 0.1, is that normalized to the tree level amplitude
Yes,
value?
yes. They were normalized to the to the A plus minus, which is the square root of B plus minus. That's right. They
Which
have
is
normalized.
dominated by tree level.
Yes, normalized not by tree level, but by the amplitude for A plus minus. The reason why the theorists did that, because there's calculating uncertainty on both of them will decrease. So they rather use the experimental thing. And so they smartly arrange the things so that small CP violation is ignored, and you end up getting the, so it's really divided by A plus minus, but this is what it is.
So when you say it should be 40 times, it should be 40 times of 0.1, is it?
Of what we are observing is 40 times, 47 times of 47.4.74 is what we had, right?
Times 0.1.
Yeah, 0.1 is what we have.
Right.
And what we are finding from data pit is 4.74. So
Right.
it's 47 times bigger.
And the tree level value would be what?
No, what they've done is they've divided by A plus minus amplitude.
No, in the same way of doing, what is the size of the tree level?
No. The point is nobody estimates the tree level size.
I see.
But that is the whole point. They said, let's not estimate the tree level, because two uncertain things are not a good thing to do. They just therefore put down this thing. So Kotipinian and Petrov did this. Now the calculation is the same old calculation with this thing, but done at charm. Kotipinian is good at this. They do extract from various things. They have in charm resonance. So let's hope that the calculation is correct. But the point is that what makes me think is that estimate of bigger than 0.1, even a P by T ratio or P plus minus, which is the ratio of the penguin to the square root of B plus minus or A plus minus, that is already looking big at 0.1. So it's very unlikely that you have 30% size, because you have the loops. So the loop effect suppressions come in anyway, right? Thanks.
Okay.
Anything else? No? Thank you.
Any other? That's.
Yeah.
So the last step of the session is by Anurag Tripathi. He will talk about patterns in scattering amplitude.
Okay, so first of all, I would like to thank the organizers for giving this opportunity to present our work here. Some of you have already heard this talk at another place, so sorry if I bore you. So I'll be talking about some patterns in scattering amplitudes. Okay, I'll be mostly talking about the color structure, color patterns. But before I do that, I want to first make a case that why QCD is important and why scattering amplitudes are important, QCD scattering amplitudes, and why infrared structure of QCD scattering amplitudes are important. So first few slides I would devote to that. So that's the first major scattering experiment by Rutherford. He was bombarding alpha particles on gold foil. And in fact, very recently I visited a experimental facility where they have, among many setups, one setup for Rutherford scattering. I wanted to show that picture, but the file became too big and I couldn't, so I had to remove. But that was quite impressive. We have that in Hyderabad, not in IIT, but another institute. So we have been scattering particles, and after we have scattered them for long enough, we realize that the nature is governed, if you leave out gravity, by SU3 cross SU2 cross U1. Okay, that's the standard model of particle physics. And in this talk, I will only be talking about SU3. So that's the experimental slide for me. Now, QCD is actually extremely important, and this slide, this graph establishes that very nicely. Imagine that this plot was not available. This was not done by these three groups, and we had discovered a peak in diphoton channel that we eventually did, and there is a signal standing there, and we have a leading order result with us, or even a next to leading order result. Okay, it would be very tempting to believe, and in fact, that would be the immediate conclusion, that what you see as a peak there corresponds to a new physics discovery. Okay, because you anyway did not know where you are going to see Higgs, right? You see a peak. Your cross section has no connection with the experimental, the measure, the calculated value. Suppose you had only leading order result or next to leading order result. So you see something very different from your prediction, and you immediately announce you have seen a new physics signal. So this slide tells you that it's not just about precision. Also, you may falsely believe something to be a new physics signal if your predictions from QCD are not precise enough, okay, because the couplings are large here. So that's why we have to be as precise in our predictions as we can, so that we can make proper understanding out of our experimental findings. So that sets the stage for me to look at scattering amplitudes in QCD. This slide is mainly for notation. A stands for amplitude, and for the number of external lines. Okay, so here it's n is 4. It could be any number of external lines, and I'm going to be talking about fixed number of lines. So all the corrections that you're going to have here are virtual. So no real emission lines coming out of those, okay, because that will change the number of lines. So I'm interested only in virtual corrections and actually in gluonic corrections. Okay, so I'm interested in QCD scattering amplitudes, but in infrared limit. So I have fixed number of lines and number of them. And when I look at QCD corrections, they are all virtual particles running around in loops. Let's look at gluons for example. I have to do integral over loop momenta, and some of those configurations will correspond to soft gluons. Okay. Now, if you have soft gluons, propagators can go on shell. They may or they may not, depending on from which line they are being emitted. And if they do go on shell, then you have a divergence. Okay. So this object is divergent. It will have poles because you will calculate in dimensional regularization. So it will have poles in epsilon. Okay, but you might say, why should I care? Because after all, in any physical observable, these poles are going to be cancelled against real emission contribution. So why should I be so much bothered about it? It's just a technical detail. Okay. So here I list the reasons, and I will also show you one result to make the case that even though these poles are going to cancel, they leave behind very important significant signatures at every order in perturbation theory. Okay. So they leave behind large contributions at every order in perturbation theory, even after the cancellation has happened, and you might be required to do resummation. Okay. If you do that, you recover predictive power. Otherwise, you have lost your predictive power. So here I'm showing how things will appear. So instead of looking at virtual gluonic emission, this K denotes a gluon here. I'm looking at a real emission. Just because the stories on both the sides are same, I'm just taking liberty to show it with a real emission diagram. So you see, if K, the momentum of this gluon is soft, then this factor, which is called iconal current, diverges because it's 1 over K. Okay, so that is what leads to these poles when you calculate. Another important thing to note here is there is a factorization of this iconal current or the contribution coming from the soft gluon from what I call as hard part, this red block. Okay, so these two pieces sit factorized, and the same happens for collinear emissions also, or collinear radiation when you're looking at virtual corrections. Okay, so I'll try to make a case using this plot. This is from my first paper on resummation from 2013 or 14. So the red curve here gives PT distribution for Higgs production. Okay, the details are not important. Which process, what, those are not important here. We are looking at PT Higgs produced in the final state and transverse momentum of it. Okay, suppose you do only a fixed order next to leading calculation. This is the blue curve that you get. Okay, so here let's say when you are at 250 GeV or 300 GeV, your result is somewhere around 10 to the minus 6. Okay, in whatever units it is, 10 to the minus 6. But as you go closer to 100 GeV or 50 GeV or so, it's 10 to the minus 2. Okay, so there's a 4 orders of magnitude difference. It's a huge difference. Now you would imagine that in experimental setup, the data is largely going to be around small values of PT because cross-section is large. So you'll be producing a lot of Higgs with lower values of PT. This is what your blue curve is telling. But it is also telling you that you cannot trust perturbation theory precisely in that region. After all, it has taken jump of 4 orders of magnitude, and it is going up, and actually it blows at PT equal to 0. So it goes to infinity if you do a fixed order calculation. Okay? So the place where your experimental data is going to be significant, you would like your theoretical prediction to match with those to make sense out of it. Precisely there, you cannot really trust your perturbation theory. Okay? And this has happened because of the contributions coming from soft and collinear emissions, which poles cancel, but the left imprint, and that imprint is showing up here. Okay, but that imprint is in a very specific pattern. And if you know that pattern, then you can look at the entire perturbation series, sum up all the terms, and get this red curve. Okay, that's a resummed curve. And you see here, now you are in good shape because you can use your experimental data and match with experiments and do whatever analysis you can. Okay, so resummation brings predictability back on the table. And for that, we need to understand infrared structure of gauge theories in a proper way. Okay, so here is the plan of the talk. I'll be talking about scattering amplitudes in the infrared limit, and I will show you how webs enter into this discussion. Then I will tell you about a uniqueness theorem that we proved and a new formalism that we gave to look at the color structure of scattering amplitudes. And then I will summarize, and the results I'm going to show you are based on this series of papers that we have been working on since 2018. Actually, there are a few more now. Now, all that I told you in previous slides is possible. This resummation, etc., is possible because when you look at the amplitude in the infrared limit, A, it's going to factorize in that form, in that limit. Okay, so it will have a piece which is called a soft function, which carries all the poles in it. Okay, then a jet function which carries all the collinear information, and a hard function which is basically a matching function. So the important thing for me in this talk is the soft function. Okay, the matrix which contains all the soft divergences. I call it soft matrix or soft function, that you can write it down as a correlation of Wilson lines. So all these external lines which are hard particles undergoing scattering, you can replace them by Wilson lines to capture the soft divergences. And here is the most important slide of this talk. Okay, even if you were to forget everything what I say, this is the important one. You want to know the divergences. Okay, the soft function carries all the divergences which are living inside this. So this has poles in epsilon. You calculate it to some order in perturbation theory, you get those poles. Okay. On the right hand side, you have an exponential of something. That exponential of something has a gamma. Gamma is what is soft anomalous dimension or soft anomalous dimension matrix, the same we study when we do renormalization. Okay. That's a finite object, depends only on the directions of these external momenta. Okay, beta i's are giving 4 velocities. Okay, this is finite. The argument of alpha s, this depends on alpha, it's a series expansion in alpha s, has lambda square. Okay, this running coupling is integrated over. So you see there's an integration over lambda, which is the argument of alpha, which is going to generate the poles. So all the poles on the left get generated by this integral. Okay, but now it's an exponential here. You do a first order one loop calculation of gamma, you get something at order alpha s, one pole, you are exponentiating it, you get infinite set of poles at each order in perturbation theory. So what you are doing is, by one calculation at one order alpha s, lowest order, you are able to, because of this formula, you are able to tell what is going to be the infrared structure at some level to all orders in perturbation theory. Okay, this is an example of resummation. Okay, so gamma is soft anomalous dimension or soft anomalous dimension matrix, and you would immediately agree that that's an extremely important object to calculate, because that gives you a control over poles to all orders in perturbation theory. Okay, so that's a central point of this talk. Here is what you get when you calculate gamma 1. Okay, there is a alpha s you have to supply, put it in the exponential, and you will be generating poles. Now, this S is the same soft function which has all the poles. This is sum of Feynman diagrams, and each Feynman diagram has its kinematic factor, corresponding kinematic factor, and a color factor. Okay, so at each vertex you have these generators of SU3, they are sitting there, so that contains the color factors. Now, this soft function can be written as an exponential of something, and that something turns out can be again written as sum over the same set of diagrams. Now, that's non-trivial. You can always write something as an exponential of log of itself. Okay, but it turns out that that log of S, again, it is a sum over the same set of Feynman diagrams with the same kinematic factors, but slightly different color factors, okay, C tilde. And that's what is the important object for me. That's what we are going to calculate. And these are the papers in which these calculations were done before us, up to 3 loops, 2 and 3 loops. Okay, and we did also at 3 and 4. So this C tilde is important. People are interested in calculating this object, and the most difficult part here is K, the kinematic piece. Okay, so we are going to look at C tilde, and I'll tell you why C tilde is going to be useful. Okay, so the soft function is an exponential of something, and that something has a diagrammatic expansion, expansion, and that can be further organized into smaller sets of what we call webs. So here is a definition of a web. It's a set of diagrams closed under permutations of the gluon attachments on Wilson lines. So let's look at this one. If you permute these 2 attachments and these 2 attachments, in total you will generate 4 diagrams. If you take any of those and do that permutation again, you will be within that set. Okay, that's a web. That is what sits in here. And here I am just expanding over all the webs. So color factor of each diagram in the web times modified color, which is C tilde, and C tilde is R times C. Okay, C is a column vector, R is a mixing matrix. So that's the mixing matrix that I'm interested in calculating. How am I doing with time? 10 minutes. Okay, I think let's go. These mixing matrices have important properties. One is that they are projectors. So R square is R. If you take a mixing matrix and sum all the elements of row, you get 0. So it's called row sum rule. And if you take mixing matrix column, any column, and each element you multiply with the corresponding S factor, then you get 0. Okay, and if you sum them up, you get 0. So here is how you find that S. So S is the number of ways in which you can shrink these gluons to the origin. So let's look at this diagram. If I try to first take this gluon to the origin, it encounters this gluon here, this attachment here and that attachment. So that's not allowed. When I push to origin, it should not encounter anything. So this one you can take first to the origin, then this one, and then the right one. Okay, or first take the bottom one here, then the top one, then the right one. So there are 2 ways, and that is what gives you S equal to 2. Okay, so that is what enters the column sum rule. And there is this theorem that you will get when you look at the eventually the color contribution coming out of it. It will correspond to a fully connected diagram. Okay, unlike here where these are all disconnected parts, this is fully connected. Now, one of the, apart from getting mixing matrices and knowing about the color structure, there's another reason why I believe this work which I'm telling you is useful. So kinematics is difficult. Okay, I'm telling about R that I'm going to calculate. C, you know. Okay, now this R I can diagonalize. So I introduce y inverse, I can diagonalize. Because it's a projector, it will be, the eigenvalues will be only 1s and 0s. Let's put that y here. Okay, and because some of these eigenvalues are 0, your I will run from this one to that one, and this is finally what you get. Okay, since I know R, I'm going to calculate explicitly. I know Y, the diagonalizing matrix. I know Y inverse, and since it is only this kinematic contribution which enters finally, probably a knowledge of Y or R can provide some simplifications on the kinematic sector, okay, which has been proved, which is turning out to be too difficult to manage. Okay, so that's also one hope that these studies will provide an indirect handle on kinematics. Okay, so I'm slightly going to change the diagram. So now the tail ends meet at origin. Okay, so instead of having this V kind of line diagram, you have this. But it's understood that the tails meet at the origin. Okay, it just makes easy drawing diagrams. That's why we have done that. So here is a result from our very first paper on this subject. I'm just quoting result for one of the webs. Okay, it has these gluons attached. you get this mixing matrix. Okay, you diagonalize it and you find that the rank of this mixing matrix is 3, and that's the exponentiated color factor, which corresponds to fully connected diagram, as I was saying before. And then, of course, there are many more webs, and this was published in JHEP. And then after we had these 2 papers, we started noticing a pattern. I'm just showing few of them. So if you look at this R, okay, this block seems to be scattered around in many of the webs. Okay, if you calculate their web mixing matrices, you'll see the same pattern repeating over and over again. For example, this R also appears scattered here. Okay, so both of these, the top ones, they do not have any zero elements in them, and they appear to be scattered around in other webs that which we calculate. And these were done explicitly, these computations, using our in-house mathematical code. And that's the only code that is available which can do calculations to these orders. So we wanted to find out what if there is some pattern to be discovered, and in that quest we found we had an organizing principle in mind, using which we found that within a web there are webs. Okay, and also we proved a uniqueness theorem that you will soon see that is very powerful in telling the structure of these web mixing matrices. So we started by classifying diagrams. So we said if S is 0, meaning there is no way to shrink all the gluon correlators to origin without disturbing other ones, then it is 0. And if you can shrink in one or more ways, you call it a reducible diagram. Okay, and then we further classified them into partially entangled and completely entangled. And of course, there is nothing for here, and these are the corresponding diagrams. And then we defined something called normal ordering. So we order the diagrams in this fashion. First, I put completely entangled diagrams, followed by partially entangled, and the reducible diagrams. And immediately, I see that the R matrix takes this form. Okay, there are some places where null matrices are appearing. And then here an identity matrix appears. There's a D matrix, about which I'll talk more. And then you have these 2 rectangular matrices appearing. Okay, so at least I know a reason why those zeros and ones are coming. Okay, I can tell you later if you are interested. And then we proved a uniqueness theorem, which simply says this: if you have a web for which S is not equal to 0, okay, and then you find out the S values for that web, and if you were to find another web, no matter at what order, okay, at higher orders also, with the same S values, then you don't have to calculate the mixing matrix. It will be the same mixing matrix as you have found at lower orders. Okay, so that's something we proved, and it is actually very useful. So as I said, even if the 2 webs are of completely different orders in alpha S, if the S values are same, the mixing matrices are same. Okay. Now we use the known properties of R and this form which we got after putting things in normal order. And then using that, we could show that this D itself satisfies all the properties that a mixing matrix does. Okay, so you find a web inside a web. Okay, and then you see if that is a web, and typically it will, it will correspond to S non-zero values. The diagrams will have S not zero. Then if you know from any lower order computation, mixing matrix, okay, which has same S values, you can take that matrix, plug it in here, that part is done. Okay, so this way our D block is known. This identity matrix, we know when it will appear. These are anyway null. These 3 pieces are still unknown. Okay, so that's what I said. So we introduced fused web formalism. Basically, this is a slide from some conference. That's why this wheel is there. So what we are doing is we are going to do some coarse graining. Okay, so here, for example, you have some diagrams from a web. These are entangled. That one is partially entangled. I just club them together to form this one. These two are entangled, connecting these three lines, so I just replace them by this correlator. This one, the top one is not entangled with the lower part, so that remains there. This one is replaced by this. Okay, so that's what we did. That's what we did, and here is the outcome of that. Okay, so I'm showing you a sample here. So we took a web. You take a web which has 12 diagrams. Okay, run that fuse formalism, and then this mixing matrix, using this fusing and using the previous ideas which I have shown earlier, you can show that all the diagonal blocks you are able to reproduce correctly without any explicit computation. Okay, so here you have a identity 2x2 identity matrix. These are null. This is a 2x2 matrix corresponding to S values, both being 1, the same here, and this is a D matrix. Okay, so I know this completely, and here you get this result from a complete explicit computation. Okay. Now we don't have control over all the elements, but just knowing the diagonal elements is enough to tell you about the rank of the mixing matrix. So I can now tell without any explicit computation the rank of the mixing matrix. Okay, which also means that I can tell you the number of exponentiated color factors that are going to sit in the exponent for the soft function. So soft function will be written as exponential of something, and that something will have objects which will have color structure of an object which is fully connected, which doesn't fall apart if you remove the Wilson lines, and I can tell you the number of those that will appear. So here we are. We started with this, and we are here now. Okay, so that A block also, all the white pieces I know, okay, either from lower order computation or they are just identity null blocks. These are the parts which I do not know, and I still do not know about them. Also, another thing that we could do was, because of this understanding, we could look at certain classes of diagrams to all orders in perturbation theory. So these dots mean any number of attachments, and we could just write down explicitly what their mixing matrices would be based on our ideas. So for this one, we have this mixing matrix completely known. Doesn't matter what order of alpha s we have. And similarly for another class, we could completely write down the mixing matrices. So with our idea of fused wave formalism, which is a fancier statement, fancier adjective for coarse graining, at 4 loops, we could predict 60% of the mixing matrices, the diagonal blocks for them, and 50% of all matrices, okay, just by doing that. Yeah, thank you. Okay. So here I summarize. Using our fused wave formalism, we can obtain diagonal blocks of R, and with that I can tell you the number of exponentiated color factors and the rank of the mixing matrix. Okay, diagonal blocks are either identity matrices themselves or something coming from lower orders. Okay. And we could also make predictions in some cases to all orders in perturbation theory. And then we later also applied to case of massive Wilson lines, which I have not talked in here. And I think it will be nice to go back and okay, I should have stopped there itself. Yeah, here. Now you see, I have a very good control over R, the mixing matrix. Not full, but quite a lot. If I had full control over R, I knew everything about R, I would have known everything about Y, and then probably I can say a lot about K, okay, the kinematic piece, which is appearing to be very difficult to at present calculate. Okay, with that, I will thank you for your attention.
Questions, please.
And that's an advertisement. You can find some things here in this physics reports. Yeah.
Does this kind of structure that you have, the exponential part also having the same structure as the normal amplitude. Does this depend on the choice of your propagator, what propagator you use? And
No, this doesn't depend on that. No.
so it can be also done in finite temperature field theory when
Oof,
one has a
I don't
little
think
bit
I-
different propagator.
I don't think I will be able to answer that. No, I don't know.
Because there the infrared divergences are also severe and one needs a resummation.
See, this is coming from factorization. Do you have factorization there also?
Yeah, in some cases, yes.
So it could be something similar should happen. But I don't remember the details which I can check and say whether it will happen or not. But that's a nice question, yes.
Thanks. So these webs, have I understood right? It's something that you've factored out as the color part of the diagram. Is it? Is that, or have I got it completely wrong?
You have got slightly wrong. So let me go to a web. Before telling what a web is, let me just tell you why we are talking. This is the soft function that contains all the soft divergences in the infrared limit of your scattering amplitude. Okay, that soft function I can write as exponential of something. Now that something is actually a set of Feynman diagrams as I write here. It's still the same set of Feynman diagrams. Okay. Now, suppose you have a large number of Feynman diagrams that are going to sit in the exponent. Now you take one diagram, one of them, and start permuting the gluon attachments. Okay, you generate, let's say, 7 or 8 of these. And so you identify which 8 are, and whenever you permute a gluon attachment in any of those diagrams, okay, you remain within that set of 8 diagrams. But there were many more. So the entire set of diagrams has now broken into smaller sets of diagrams which are closed under these permutations.
Okay.
Each such set is a web.
Is a web. Now I understand.
And it
Okay, okay.
has both the kinematic part
Okay.
and the color part, modified color part.
Has, okay. My second question is, when you say that the collinear and soft parts factorize, is there no term which has collinear divergence times soft divergence? There
There
will be
is.
there, right?
There are. So here, that is why.
I mean, not at leading order, but at higher orders. So it's obviously.
See, these are what gives you double poles, right?
Yeah, correct.
Even
Yeah,
at one loop.
correct.
So here you see this jet function, for example.
Yeah.
That is capturing a collinear part.
Mm.
Okay. But soft is also here in Ji and
Correct.
also here.
Yeah.
So that's why you have divided the jet function by the iconal part to
Yeah, so
remove the
then-
double count.
Yeah, so that then my question is that even then this web thing works, is it?
You-
The web thing doesn't care about whether you have collinear or soft divergences, is it?
No, it is about soft.
It's about
See,
soft.
this
Okay,
this
okay.
expression is for soft.
I see.
So
Okay.
collinear will have its corresponding thing, but
I
this is all about soft.
So, okay. Thank you.
This exponent of the soft function, you have to include all the diagrams, right?
Sorry, say again.
When you have to write this S soft function as exponential of gamma matrix.
Yes.
So there you have to include all the diagrams.
Okay, go ahead.
So I want to ask, like you said, you have to take only gluons in the loops. You can take quark loops also.
Yes, there will be. I am looking only at gluonic contributions.
That
In-
means you are not looking at full S, you are looking at sub part of that S.
Yes, so I'm not looking at soft quarks.
Mhm.
Okay. Soft gluons are going to give you the leading contributions. Soft quarks give you
But it can give
subdominant contributions. Okay, so I'm looking at leading.
because there is in the propagator there is P upon P square. That's why.
Yeah, so you can take, for example, any diagram which has a quark line coming out, and you will see that when you do the calculation, that the fact that you have a U or a U bar sitting there provides an additional factor of additional numerator. So your naive power counting of having a K below
Mhm.
is disturbed because of the U's,
Okay.
which is not case for gluons. So let's say 4 gluons attaching, and then there's a quark loop in there.
Yeah,
Yeah, that will be in here.
it will be subleading in lower order in alpha S, but they are still dominating some. There should be enough contribution to soft function, no?
See,
So it is coming from some loops of the.
you see, yeah, so
said
if
that
you,
is equal to zero.
if you see here, there is nowhere, so all I have cared about is the gluon attachments on the Wilson lines. And that is why I had, I'll show you these blobs. It doesn't matter what is happening within the blobs. Okay, it cares only about these attachments. So in the entire calculation, nowhere it is relevant what is happening within the blobs. So that I can put in here, you'll still get the same mixing matrix.
Yes.
So, we had, we had pizza during the coffee, and that was sponsored by a colleague, ex-colleague of mine, in memory of Rajaji, because when he was in Chicago, he would always have pizza every day. And so it is in his memory that the pizza was there. And it's a very nice gesture of to sponsor this pizza. Thank you. It's and thank you to her. It did seek permission from her. When she sponsored pizza earlier also.
I see.
think anyway, exactly. Wait for that. So Thank you. Okay, it gives me great pleasure to invite Professor Gautam Bhattacharya to give this popular talk on the Higgs boson, on history of the Higgs boson. So for the few master students and undergraduate students I see who don't know Gautam, Gautam did his PhD from Calcutta University. And in fact, so he's a phenomenologist. A phenomenologist is a person who takes a theory of particle physics and tries to extract some information or predictive content, which can then be compared to the data in any experimental lab. And Gautam actually worked at CERN in Geneva, where this Higgs boson was discovered in 2012. So it gives me great pleasure to invite him to talk about the Higgs boson. And thanks to the TAP invitees for coming to this talk as well. So Gautam, start.
Okay, thank you, Indu. It's working, no? Yeah, okay. So it's a great honor for me to have got this invitation. I don't get many invitations these days, so I welcomed it. But I must say, on a sad note, this is the first time I'm giving a talk without Rajaji sitting on the front row with a reassuring smile. I mean, someone, I mean, I wrote our Rajaji didn't belong only to IMSC, belong to the community. I mean, we all called him Rajaji with love, with respect, with as a leading light in our community. So, well, I mean, we'll miss him. I mean, we'll miss Rajaji's presence here. Now, well, I mean, it will not be that much of physics that I'm going to tell you. So, I have a few slides, but it will be better if you rather listen to me than look at my slides. So, it will be more like in the spirit of storytelling rather than giving you, physics insights. I mean, because 99% are probably from this conference who know much more than I do. I'm little out of contact with modern status of Higgs physics, which I got to know from Kajuri today, and a few more talks by some of the younger community members. You see that I'll take you back to 1920s, 1930s, 100 years ago, and I'll show you some of the faces you probably would definitely identify as your known faces from from many books or some other references. You can see it's a Solvay Congress. You can see Heisenberg, Jordan, Max Born, Lisa Meitner, Planck. You can see Oppenheimer here. This is Meghnad Saha. Somewhere this is Homi Bhabha, Niels Bohr. I'll take you to what was happening in those days. So it's not out of place to show you this photograph. Well, 100 years ago, Maxwell's electromagnetism, which was a description of light as electromagnetic waves, special theory of relativity, which told us that mass is equivalent to energy, and quantum mechanics, which explained the stability of the atoms and a quantitative description of the atomic spectra. It worked very, very well. Now, Dirac equation, which according to Dirac was smarter than Dirac himself, for many reasons that I'm not going to, many of us know that, the equations sort of presided over, it solemnized the marriage of quantum mechanics with special relativity. Now, out of these three pillars, namely quantum mechanics, special relativity, and Maxwell's electromagnetism, on the basis of these pillars, in the early 1930s, the quantum electrodynamics was developed. Now, in quantum electrodynamics, the vacuum is not empty.
well, I'll come to that, and an experimental proof of the description of why and how vacuum is not empty. I'll mention about it. It is full of, I mean, sort of transient ephemeral particle antiparticle pair that are momentarily created and destroyed, because for a very short interval delta t, so according to uncertainty principle, the energy momentum need not be conserved. I mean, so caching that hypothesis, it turned out that in quantum electrodynamics, there is a problem, and I'm going to tell you about that problem, the problem about the vacuum. And do not ignore the power inside the atom. As you can see that the binding energy is in a hydrogen is what, 13.6 electron volt, which means that within 10 to the 10 meter, you have a potential difference of 10 to the 10 volt, of 10 volt, right? So it is like a gradient of 10 to the 11 volt per meter. Compare that with an accelerator, which is 10 to the 7 volt per meter. And like here in my watch, you have a, in your watch, you have a battery, which is like 1 volt separated by maybe a few millimeter, which is like 10 to the 3 volt per meter. So you see that it is very important to probe inside the atom, because there is a high, gradient of potential, and we will see the power of the vacuum. Okay. Now, in 1929, Wolfgang Pauli, a leading physicist in Zurich, got a remarkable postdoc from US. Well, those are the days when people used to go to Europe to do, cutting edge research. So this guy was extremely smart, very intelligent, very fast in the calculation, but sometimes, prone to making mistakes, but still, I mean, a remarkable postdoc. His name was James Robert Oppenheimer. Pauli told him, he was a research assistant of Pauli. So Pauli told him, you calculate hydrogen spectra not using Dirac equation, using quantum field theory. Okay. Now, Oppenheimer's calculation had to take into account that an electron comes and it emits momentarily a photon and it reabsorbs it. And it can happen in many different ways. The intermediate photon can also split two electrons and they will recombine, all sorts of combinations they had to take into account. So in 1929-30, Pauli and Oppenheimer were doing that calculation and they expected the result to converge. To their dismay, it diverged. The result was infinity, because they had to take into account all possible combination, all possibilities, and at the end of the day, the sum turned out to be infinity. That was in 1929-30. Well, I mean, 18 years later, in 1947, and a world war later, in 1947, in a conference, which is a Shelter Island near New York, Oppenheimer convened that conference. I mean, he was chairing a session. He was the organizer. Now, this conference was very important. It turned out to be one of the most influential conferences of this century for many reasons. First, in that conference, it was established that particle physics requires language, and that was proved to be quantum field theory. Without quantum field theory, you cannot describe particle physics. Before that, I mean, it was not so very clear. I mean, you need a prescription and a formalism, and that was quantum field theory. That is number one. Then that was a conference where after many years, maybe 7-8 years, physicists were meeting without someone peeping on their backs. Is it classified? I mean, before that, I mean, there was a lot of, around during the war, you could not meet. I mean, there was a lot of embargo. They couldn't meet and talk freely about science. And this is after, of course, the Manhattan Project, the bomb was dropped and all these things. So in 1947 Shelter Island Conference, the German physicists and American physicists and, those Germans who were in Britain, who took shelter after the war, Churchill famously said that, I mean, we will win the war because our Germans are better than their Germans. So they are all meeting in Shelter Island Conference. And another thing that sort of shifted the center of gravity of modern physics from Europe to US. That was the beginning of the American story, Shelter Island Conference. One of Oppenheimer's students, Oppenheimer was a theoretical physicist, and his student, of course, started his PhD in theory during the war. The student got involved into Manhattan Project. His name was Willis Lamb. Using the technology of microwave radar that he developed during the war, Lamb measured a splitting of, between two lines in hydrogen spectrum, which is 1 part in a million. Okay, which according to Dirac equation, those two lines should have coincided. But he measured a splitting, and that was 1 part in a million. And he reported that in the opening session of that conference. That was Lamb shift. In the same conference, Isidore Rabi, who already got Nobel Prize for his discovery of nuclear magnetic resonance. He was an expert of anything related to magnetism, related to atomic and nuclear spectra eventually. So he got it in 1944, got Nobel Prize in 1944 for NMR discovery. So he came with a report of a measurement of the Landé G factor, G in excess of 2 by 1 part in 10 to the minus 3, in 10 to the 3, so 10 to the minus 3, but non-zero, 0.1%. Now you have to explain it. So there were physicists like John Wheeler, then Swinger, Feynman, young physicists like Swinger, Feynman, and Feynman's supervisor, John Wheeler, was there. Swinger's supervisor was Rabi, he was there. Hans Bethe was there. So there were a battery of, the top-notch figures in theoretical physics and experimental physics present in that conference. So Oppenheimer gave a task. He was a taskmaster. He gave a task. You have to calculate this Lamb shift in using the language of quantum field theory, and infinity, which he got, well, some calculation he tried to get, would not be accepted as an answer. Neither 0 or infinity would be accepted as an answer. So that was the task. So Bethe did the calculation, well, and Swinger and Feynman were also doing the calculation. So they found some non-zero. I'm coming to that. And Swinger also calculated, his supervisor measured G minus 2, so he calculated G minus 2 also. So what came out is a remarkable story. So they found that why they were getting infinity. They were, they were calculating all sorts of possibilities, like the electron emitting a photon and reabsorbing lights, like a snake eating its own tail, and that way getting infinite amount of energy because of all sorts of possibilities leading to infinite amount of energy attributed to the electron, and the electron energy is equivalent to mass, so the mass was shooting up to infinity. So what they found, that you need a reference point. Okay, with respect to that reference point, how different is the other thing? So electron mass was a God-gifted quantity. Somebody has measured electrons mass, and that is finite. Okay, somebody has measured electric charge, and that is also finite. So they found that the infinities that are coming to the calculation of the mass and the electric charge are very similar in analytic expression to the infinity that is coming in the measurement of the Lamb shift, in the theoretical calculation of the Lamb shift. All were infinity. So if you assume the experimental value of electric charge and electron mass as the quantities that somebody had given you, and with respect to which you put the experimental numbers, so replace the theoretical expression in terms of the experimental numbers, and in terms of those experimental numbers, you try to calculate Lamb shift and G minus 2. all came out to be perfectly sensible. I mean, this is very simply I put it, but the whole thing about, using a reference point of some experimental quantity, experimentally measured quantity to calculate something else was technically known as renormalization. So quantum electrodynamics turned out to be a respectable theory at that time because of Feynman and Schwinger. They did the calculation in completely different ways. Schwinger did it was kind of the old, Sommerfeld school of training, that you do the calculation pedagogically, step by step, pages after pages, and finally come up with a number. Feynman used some trick which nobody believed. People said he's a magician, he's a cheat. So, but at the end of the day, the results were matching. So in that conference, they made it to, that things worked perfectly well. So Tomonaga did it independently. So Feynman, Schwinger, Tomonaga, they were credited with the discovery of this renormalization prescription and putting QED on a respectable platform, for which all got Nobel Prize. Now, what is QED? Quantum electrodynamics, it's a gauge theory, which means gauge means phase. So the thing should be invariant under some your equation should be invariant. Dirac equation should be invariant under the phase transformation with the phase of the electron. For example, you put a phase transformation of the electron, and if the phase is a constant, then of course Dirac equation is invariant. But if the phase varies at different point in space and in different instant in time, then of course the equation is not invariant. Okay. Now if you want your system to be invariant under the transformation, you have to do something else. Just to give you an example, consider a circle. Okay, a circle. Now, if you rotate each point on that circle by the same angle, the circle remains a circle, right? But if you rotate different points of the circle by different angle, then of course the circle is deformed. Then if you want the circle to remain a circle, you have to do something else. You have to introduce some other force to counter what was that deformation at each point, right? So what happens if your phase on the electron is different in different point in space and time, then what you have to introduce is what is called the gauge field, which is the photon, which is like a fabric it's like elastic fabric that stretches everywhere. Okay, and its role is to correct for the deformation. So something you deform just because of the transformation, and the photon or the gauge field will have to adjust itself, will have to transform itself accordingly so that things remain exactly like before. So the basic principle, the gauge principle, necessitates the emergence of this force of the photon. So it's an emergent thing, and it has to be necessarily massless. Without that, you cannot explain the invariance of the system. Okay, so photon is coming out naturally. It's a massless photon. Okay, so that is what they were and that is an important criteria, this masslessness, in order that you can calculate those parameters like G-2 or lamp shift precisely to the satisfaction of the experimental results and theoretically consistent way. So masslessness is a very important criteria for that. Okay. Now, during the 1950s, a few years later, Frank Young and C.N. Young, I mean, you know that C.N. Young and T.D. Lee, they're two students, very bright students. They went to US for PhD. And by the way, I mean, this is something I heard from one of the senior physicists many years ago when I was probably your age, Pasha Kabir. I mean, I don't remember where I heard this story, but he was a postdoc. He was Bethe's student, and he was a postdoc together with Weinberg and Feinberg in that group. So, so he told us that no, in what context I'm telling you this thing. I mean, I'll come back to that. I mean, I missed the thread in which context I'm telling you. I'll come back to that. But anyway, so this Young and Lee, so they didn't get the visa to go to US directly from China. Okay, after the war, so they had to go through India. So they had from China, they came to Calcutta. From Calcutta, they went to Bombay, and from Bombay, they took the ship. So Young had malaria in Calcutta and spent 1 month there. And so one of the things they had to go through India, Saha wrote a letter to Fermi in support of their fellowship for the PhD student. They were going to Chicago at that time. So that's what I heard from Pasha Kabir. They had malaria. So I don't know. This is what I heard from Pasha Kabir. I mean, to what extent it is true or not. I didn't read it anywhere else, but it's an interesting story I shared with you on a lighter note. So Young it was in 1954 or 55. He was visiting Berkeley, and there Mills was there. Robert Mills was also visiting. So they shared an office and they started discussing about physics. So their goal was to generalize this QED. So it's for electron, no? It's electron and photon. So they were thinking about strong interaction, but to include strong interactions, you have to include both a neutron, N and P, neutron and proton. So 2 objects. So for 2 objects, a single photon, or it's not just 1 electron. So you have to transform a column vector of 2 objects. So it's basically it's a doublet. So you need SU2 matrices. So you need higher groups, Lie groups. Okay. So they were playing with an arbitrary group. I mean, like not SU1. SU1 is U1. I mean, SU2, SU3, and so on. So for SUN, they did the same algebra. Okay. They were actually planning to explain strong interaction. But they found that, of course, I mean, neutron and proton are, one is charged, the other is neutral. So there will be more photon-like objects, and one will take neutron to proton, which means that is electrically charged. But necessarily they have to be massless, because that is the gauge invariance. But there is no such charged particle, charged object, spin-1 object, which is massless. So it's mathematically beautiful, but realistically it's bogus. So that was their conclusion, but they didn't leave hope. I mean, Young used to always think that if something is beautiful, it has to be correct. So he was just waiting. So they didn't throw this thing, I mean, but kept in mind. In the meantime, weak interaction was coming into the picture in a more kind of explicit and strong way, in the sense that people didn't believe about weak interaction before. Of course, radioactivity people have seen, but now people have started explaining, for example, why we get daylight, like sunlight, in the interior core of the sun. The strong interaction binds 4 protons together. It's a tight clump of 4 protons. Then it's weak interaction which convert 2 of the protons to neutrons, and then you get a helium, and then with some energy, and that photon sort of bounces back and forth inside the core of the sun, and 100,000 years later they come to the surface. 8 minutes later they come to you. So the role of weak interaction was getting increasingly more clear. And of course, beta decay was something that was remarkable, because I mean, I think Fermi was asked in his deathbed that what did you think to be the most interesting and special thing in your career, puzzling thing? Of course, he could have said many things, but he said beta decay. I said, why? Because electrons are coming from the nucleus. I mean, that is something that is puzzling. Electrons are in the outer shell. Why they are coming from inside the nucleus? So you don't think that you see that there have been relativity, general theory of relativity was also there, but Fermi didn't think how much stress they put on experimental discovery at that time. The electrons coming from the nucleus, and that couldn't be explained. Although Fermi tried to do it, but of course, I mean, he was also not satisfied with his theory. So, but eventually in 1957, weak interaction was kind of proved to be of V minus A nature, vector minus axial vector nature. And one of the former directors of this institute was involved, Sudarshan, with his supervisor Marshak, proposed this V minus A nature of weak interaction together with Feynman and Gell-Mann. And so people started thinking, okay, so if weak interaction is of vector minus axial vector, by the way, Salam also thought that it has to be V minus A, but Salam was always in contact with the experimentalists. So he got some preliminary data. So they would believe the preliminary data. So the preliminary data suggested it is S minus T, the scalar minus tensor. So Salam by that time submitted his paper to physical review. He withdrew it. Okay, so V minus E paper he withdrew and he submitted S minus T paper. So he missed the bus. But many people were, doing, so the data eventually turned out to be V minus A. Nobody got Nobel Prize for that. But, the idea, some people were getting the idea that if weak interaction is of V minus A nature and electromagnetism is, vectorial, right? So there may be some connection. So why not try to find a common source from where you are getting weak interaction and electromagnetism and some kind of a unification. So around that time, I mean, late 1950s, in 59, 60, Sheldon Glashow, whose name I'll mention later, he joined for his PhD with Schwinger. And once, I mean, this is the beauty of having many stalwarts in your institute to give talks. So Murray Gell-Mann visited Harvard at that time. And after his seminar, after some discussion, Murray Gell-Mann suggested Glashow, why don't you, think about it, that how to unify electromagnetism with weak interaction. So Glashow later said that, okay, I only thought about that issue for 2 years, and his PhD thesis was a paper marrying electromagnetism, that is SU2 cross U1 paper, without, of course, the mass generation mechanism, where all the gauge bosons apart from photon will be massive. So that was his PhD topic in 1962. Coming back to this V minus A nature, it is clear that you can use one of those gauge boson, charged gauge boson, to explain beta decay, because neutron has to go to proton, and then so it's mediated by, today we know it's called W boson, some charged goes, but it has to be massive. I mean, otherwise nuclear, it will not be confined within the nuclear domain, right? But if you give mass, then you're throwing the baby with the bathwater. Essentially, your masslessness is an essential criteria of gauge invariance. So how do you reconcile the masslessness that you need to have a consistent theory and the demand that the photon-like object, which is a charged object, has to be massive? I mean, this was a massive question. In fact, Young gave a seminar on V minus A on beta decay. Essentially, beta decay he was trying to also explain. And Pauli was in US, and Pauli was in the front row. So Pauli asked him, but what about the mass? He said that no, now we don't know anything. Actually, Young was giving a talk on Young-Mills theory, okay, and whether it can explain beta decay and so on. So what about the mass? No, we don't know about it. Then Pauli dismissed it. I mean, then he at some point of time, Young had to, go back to his seat. He couldn't continue the talk. Suppose you ask me a question, fundamentally, I can't answer. I have to sit down. I can't continue on the talk. That was the main point. I mean, that so then Oppenheimer said, let Frank proceed. I mean, then he could complete his talk. And then, Pauli wrote him a letter that you made it impossible for me to talk to you. Pauli was absolutely nasty with him, but okay, I mean, you carry on, something like that. So those were the time when you today, I mean, on a day, all of us put, you know, arbitrary number of particles in our mathematical calculations with arbitrary charge and say that let it be experimentally tested. In those days, it was very difficult unless it is already, you know, I mean, it has a convincing reason to exist. I mean, so the question was how to generate the mass without losing the thing that we gained, that we tamed the infinity by having a massless particle which follows the gauge principle. But now realistically, we have to generate the mass. That was a massive question. Okay, you got it. More or less parallelly, people were discussing about some other thing, apparently unrelated, but they would be related in a big way. The role of symmetry. Okay. Now, it is important to study it because they realized that this big question. Well, it was not. It was there was no mathematical proof, but people had this kind of a eerie feeling that maybe it is a holy grail, that at the end of the day we would be able to join two problems. They're independent I'll come to this problem, to two problems, whether they can together they can give you a solution. That is the reason I'm talking about this idea. See, that you think about let me tell you, I mean, there is a symmetry, no, on this dinner table, that if you sit there, you can choose your glass either on the left or on the right. There is a symmetry, right? Now, the moment any one of you chooses the glass on the right, then all of you will have to choose the glass on the right, and vice versa. The symmetry is broken the moment you take a decision and choose on the right. Okay. Think about, so the symmetry is broken. Now, think about water molecules in normal temperature. It has a perfect three-dimensional symmetry of the water molecules. But you go to sub-zero, you will get snowflakes. For example, this snowflake has, you know, I mean, has a symmetry that if you rotate it by 60 degree, you get the same flake. It's a discrete symmetry. So it's lesser symmetry. It's not, it's less than the three-dimensional rotational symmetry. So if your experience is limited to sub-zero temperature, you will not know that water molecules have a three-dimensional symmetry. You will see the flakes and you will conclude that it has only discrete symmetry, which in this case is you know, rotation by 60 degree and so on. It could have been a different shape as well. So we say that the symmetry is spontaneously broken. Okay, okay, what do I mean by? I'll slowly explain what do I mean by that. Spontaneous symmetry is hidden in the sense that you are looking at a particular solution in a sub-zero temperature. You don't know the full symmetry. You don't know how, what are the laws of that govern the motion of the molecules, water molecules. The laws that govern the motion of the water molecules have a full three-dimensional symmetry. But in a particular phase, which is the solid phase, you see a lesser symmetry. Okay, so the question is that sometimes by looking at the solution, you should not judge the symmetry of the equation of motion or of the system that governs the motion of the particles. I'll give you another example, like ferromagnetism. No, the magnets are aligned, okay, but around the critical temperature, the higher symmetry goes to a lower symmetry when they are all aligned. Right? I mean, the tiny magnets, they are all aligned in one particular direction. So if your experience is limited to that phase, you see lesser symmetry. But if your experience, but it's pure electromagnetism, which does not have any sense of direction, right? Now, I'll give another example. It is not necessarily confined to subatomic zone. Okay, in classical physics, way back in mid 1600, a French, well, I mean, polymath, I would say, his name is Boulouardis, and Robert Hooke, who was contemporary of Newton, they all anticipated this inverse squared law. Okay, but what they didn't, but they couldn't convincingly say that it is valid also for planetary motion. Why? Because Kepler's laws of planetary motion tell us that the orbit is elliptical, right? But if it is a inverse squared law, it is a radial thing. Why it is not spherical? Okay, it should be perfectly spherical if it depends only on the distance and it is 1 over r square. What Newton conceived is that these planets have initial velocities. So their elliptical orbit is not in contradiction to the inverse square law, which is perfectly symmetric. So which means by looking at the solution, which is the elliptical orbit, you don't try to gauge the symmetry of the equation of motion. So symmetry was spontaneously broken in the solution. The similar thing happens in superconductivity. Okay, I'm slowly coming to the point where I'll discuss about the generation of the mass. So in superconductivity, what happens? Okay, so let me tell you that if you drive through a tunnel, for example, okay, the tunnel has a lot of metal, no, on the wall. So you see that your radio signal is disturbed. Okay, but if you have a compass, the magnetic needle, that still points to the north. So essentially, a conductor, it expels electric field, but is opaque to it doesn't do anything to the magnetic field. But in a superconductor, both electric fields and magnetic fields are driven out. Okay, so I mean, since photon is a carrier of electromagnetism, it can penetrate only a thin layer of a superconducting surface, and so it appears to you that it has a short range interaction because it doesn't go inside because of the Meissner effect. So it appears to be massive inside the superconductor. So superconductivity gives you a handle to try to understand that a photon might become massive because it has a short range interaction. That's the indication. So what exactly happens that suppose an electron is coming to a lattice of ionized atoms. Okay, it passes through and it gets attracted, because of the charge of the atoms, ionization charge. When the second electron comes, it sees a distorted lattice. So inside the superconductor, if the two electrons come what is called closer to Fermi surface, I mean, so they act collectively. I mean, they attract each other magnetically, so that a combined object of two electrons very close to what is called the Fermi surface, they cancel their magnetism and become an object which is like a pair of two electrons called the Cooper pair, which does not have an intrinsic spin. Okay, so the symmetry is spontaneously broken. So what exactly is spontaneously broken? I mean, think of a two-dimensional vector with the real part and imaginary part of the electron field. In electron field, I mean, it's basically the operator that destroys an electron in quantum field theory. So the real part and imaginary part make a two-dimensional surface. A 2D rotational symmetry was there in the beginning. And once Cooper pair is formed, what is left is a discrete symmetry, which is a rotation by 180 degree, which basically means E to minus E. So that means that even number of E's can make a pair. Okay, so very important thing is the original symmetry and the residual symmetry. So in fact, BCS paper discusses about the approximation that if the two electrons are very close to Fermi surface, okay, some very close to each other, then they form the Cooper pair, and with that approximation you can actually calculate zero electrical resistance expelling the magnetic field Meissner effect. So if you talk to a a field theorist like Weinberg, he would say, well, now we have to meet him somewhere else. He would say, no, I don't want to use that explanation to explain the exact properties of zero electrical resistance. It is not close to zero. Zero electrical resistance and total expelling of the magnetic field like Meissner effect by some approximate thing. I would use a symmetry. So the symmetry and the residual, the remnant symmetry is very important. With that, I told you the symmetry is a two-dimensional rotation in the real and imaginary plane of the electron field, and the residual symmetry is 180-degree rotation after spontaneous breaking of what is spontaneously broken is electromagnetism, and it appears that photon is massive. Okay, so then Anderson conjectured that so these two things that that how would photon become massive? Something is lost. What is lost is when symmetry is spontaneously broken, then a massless spin zero object will come out from the mathematics. So Anderson conjectured, but we don't see that. There is no there is no mathematical proof at that time of when Anderson was doing it, for a reason. There cannot be any mathematical proof for that. He was thinking about it, that some kind of cancellation mechanism is there, so photon appears very massive. Now Nambu thought that, okay, this is a good idea, so why not think the universe to be a superconductor? And what happens when the Cooper pair breaks? Okay, it liberates energy, and the two electrons have more energy than before inside, because the binding energy is shared by the two electrons, and since energy is equivalent to mass, so those electrons appear massive. Okay, so Nambu had the idea that let the universe be considered to be a superconductor. So originally the nucleons are massless. So so then after breaking of some symmetry, well, he actually conjectured that it's called chiral. Chirality means hand. Some symmetry which has to do with the handedness. I mean, okay, some kind of a global symmetry. When it is spontaneously broken, the nucleons become massive. Okay, so that was in the late 1950s, early 1960s, and Nambu said that. And based on Nambu's paper, Goldstone gave a solid mathematical proof that whenever a global, it has to be global continuous symmetry, not discrete symmetry, is spontaneously broken, there would be massless spin zero objects. You cannot bypass that. And the number of such objects depend on how many, how the symmetry is broken. Okay. So he gave a mathematical proof. So those bosons were, were called the Nambu-Goldstone bosons. Nambu conjectured it only in the case of chiral symmetry, but Goldstone gave a detailed, explanation. Then Nambu and Jonah Lesogino, they wrote a paper that in superconductivity, well, without much mathematical proof, there is no massless spin zero object. So it must have been absorbed by the photon, and so photon appears massive inside a superconductor. Okay, so I mean, what turned out to be a problem that you don't see any massless spin zero object, and there is problem number one, and problem number two is that you require massive spin one object. So the question was how to reconcile the two. I mean, those two problems are independent problems, or think of it as in a unified way. One is a solution to the other. That was the attempt that people started doing at that time. So in the next slide, I mean, is that I have some mathematical formula, but that's the only mathematical formula I have here. That if you, for example, move along this orbit, you don't it doesn't cost any energy, and that is the oscillation of this massless particle. Okay, so the massless particles move around this orbit, and they are in the exponential of the original scalar field, and there is another spin zero object which is an excitation in the radial direction, just along from that radius. If you consider that excitation, the radius in that plane is v. Okay, it's a constant mass dimensional parameter, and this radial excitation is what is this Goldstone's other boson. I mean, that is what would turn out to be the Higgs boson eventually. So remember this, and this is the only mathematical formula I have in this theory. So I told you that what did Anderson, how much time will you give me? Okay. Huh? Okay. So what did Anderson tell us? That in the superconductor, somehow the so-called massless spin zero object, I mean, this Nambu-Goldstone boson is missing, and photon appears massive, and some kind of a cancellation mechanism is there. It's a conjecture without any mathematical proof. Okay. So then this Klein, Oscar Klein and Bentley, it's not T.D. Lee, Bentley, they said no, superconductor is it's a non-relativistic system. It's a finite system. You cannot use special relativity there. So there it is okay. I mean, they gave a proof that in a non-relativistic system, you don't get any Goldstone boson. Okay. And then there was a guy whose name is Walter Gilbert. He started his PhD with Nick Kemmer in Imperial College, and Nick Kemmer was the PhD supervisor of Salam. But somehow Salam, sort of captured him, and Gilbert started working with Salam, but he was more or less independent. So Gilbert gave a proof that what Lee and Klein said, that it is so in a non-relativistic system, you don't expect any massless particle, spin zero object. But this idea can be, this argument can be advanced also for a relativistic system. So Gilbert said no. He gave a formal proof that no, in a relativistic theory, if global symmetry is spontaneously broken, you cannot bypass a spin zero. The spin zero object, spin zero massless object has to be there. But in nature, there is no such thing. So it's an impasse. I mean, it's a roadblock. Okay. So Gilbert by that time got disinterested in continuing in particle physics. So on the same, so he went to Harvard, and he met Watson and Crick in the same corridor where his office was, and he got interested in DNA and in the molecular structure and the helical structure of DNA and so on. And in 1980, he got Nobel Prize for his work on DNA in chemistry or in life science chemistry. And he was also famous because he started this Human Genome Project. But Gilbert's paper in particle physics, that was his last paper in particle physics, that launched Peter Higgs. So Peter Higgs, so Gilbert went from particle physics to biophysics. Peter Higgs started his he did his PhD in biophysics. Okay, molecular aspects, and he came to he came to Cambridge at that time, and he was probably a visitor or I do not know, postdoc or whatever. And he went to Imperial, he met Salam, he started discussing, and they went to Scottish summer school and where, he got this idea, because there you met you meet all the other people thinking along the same direction. He got interested in particle physics, and he was very curious whether I can beat Guralnik in the argument, because Guralnik's argument didn't have any loophole. So you have to have massless spin zero object. No way you can escape that. Okay. So he was thinking about it. At the same time, I'll come to what Higgs did a little later before I give another example. So Higgs was thinking how to bypass Guralnik. Gilbert. At the same time, in Imperial College, no, not in Imperial College, an American physicist, his name is Brout. He got a Belgian postdoc, his name is Angler, and both of them were interested in Kant's matter physics. So they were thinking about, again, the symmetry breaking, but symmetry breaking in the spin chain. Okay, so suppose you have the spins perfectly aligned, but they also precise. No, there's a spin. So you can think of nearest neighbor interaction, and the way there is a periodic motion of the of the pattern in which the tips are moving. You can see some periodicity. So actually, in the context of spin waves, you can consider that to be the Goldstone mode, the mass less mode. Okay, so it's a nearest neighbor interaction. If you think of, so it is the infinitely long wave. I mean, that would be your Goldstone mode. But then if you go beyond your assumption, initial assumption, it's a nearest neighbor, you start taking interaction of the next to nearest neighbor and so on. Okay, it will be so random that the Goldstone mode would disappear. Okay, so they got this idea that if you think of long range force, which means you are not confined to nearest neighbor interactions with all the particles, all the spins in your neighborhood and beyond, which is a long range interaction, then the Goldstone mode disappears. So is it in electromagnetism, the Goldstone mode, electromagnetism is a long range force. So can I apply that to electromagnetism, that the Goldstone mode would disappear, and we see what happens to the photon? Okay, so where does the degree of freedom go? That is the question. Okay, so then they wrote that paper in sometime in the early months of 1966, that if there is a photon and there is a symmetry breaking, then the photon becomes massive and the Goldstone boson disappears. There is a cannibalism, means the photon absorbs the Goldstone boson and becomes massive. Okay. A few months, okay, so Higgs went to that summer school, and somehow he got the idea. I mean, he later claimed he got the idea there that the same thing, that absolutely the same thing, that the mass generation mechanism is solved. Gilbert's argument can be bypassed. That Gilbert did not say that what happens in a gauge theory. Gilbert's argument is correct. If there is a global symmetry breaking, you cannot bypass the Goldstone mode. But if it is a gauge theory, in a gauge environment, it is possible that the photon becomes massive. So he did the mathematical calculation exactly like Brout and Engler, and the Goldstone boson disappears, and the cannibalism works, and the photon becomes massive. He sent his paper to physical review letters, no, to physics letters B, or in those days probably physics letters, there was no A and B, and it got outrightly rejected. Okay. He was at visiting CERN, and if you are at CERN in those days, you have to send your paper to an European journal. So paper got rejected. So he got dejected. He sent the paper to physical review letter. In the physical review letter, the referee said that everything is fine, But what happens to, I showed you that sigma, the radial mode of excitation around, what happens to that mode? Nobody was interested in that mode. Nobody was interested because the mass generation is the most crucial issue, how to save, renormalize, how to save the invariants, gauge invariants and so on. Nobody cared about what happens to that, object which has, whose coupling is unknown. Well, I mean, it's parameterized only, nobody cared. So, but this referee, I mean, allegedly Nambu, insisted that you write something about the properties of that particle. So he wrote a few lines on that radial excitation. That makes him different from Brout and Angler. And Higgs was also not involved, I mean, not interested in that radial excitation. That would be the Higgs boson. Okay. Now, a few months later, 3 people in the Imperial College, Guralnik, Hagen, and Tom Kibble, they were also thinking about the same direction. They received the preprints of Higgs as well as of Brout and Engler, and they did not take it. Kibble later said he didn't take it seriously because the logics were not very tight. There was not much discussion on the degrees of freedom. So they were trying to give a more robust proof of the same thing. Within 3 months, they wrote their paper, which is the best paper because it has logically the most consistent and which takes into account the degrees of freedom, what happens to the degrees of freedom, but it's the same thing. It's the cannibalism paper for a photon, for how photon becomes massive. But no discussion on the radial excitation. Only Higgs was forced to write about it by the referee. Okay, so these 3. So later on, they regretted why, for learning it in a much better way and writing the paper in a more systematic and concise way, they wasted 3 months. Okay, so again, I mean, one more thing I should mention, that still it was not a proof that the theory is renormalizable. I'll mention a few lines on that. Okay, so the radial excitation exists. On the same corridor, Guralnik, Hagen, and Kibble were working. Salam and his collaborator, John Ward, were working on marrying weak interaction with electromagnetism, something similar to what Glashow had done in 1962, but this is 1965, 1966. Okay, so Salam and Ward were world experts of renormalization. So they knew very well. I mean, Salam actually didn't take Glassow's paper seriously, and he never, I mean, once he categorized some people to some level, he never, I mean, changed his opinion about that person. So he never read Glassow's paper after that, and he regretted. So again, they were working on SU2 cross U1, the right model to marry electromagnetism with weak interaction, so that you get the photon as well as the neutral object. That was again an embarrassment. Where is that neutral Z boson eventually? That would be found to be a reality, but it's a photon-like neutral object. I mean, what was the necessity? At least with W, you can explain beta decay. With Z, what you will do? They were embarrassed, but still they had this. And at the same time, Guralnik and Hagen had no clue how to marry weak interaction with electromagnetism. If they have talked, I mean, Imperial College had all the ingredients at that time. Okay, so in well, I mean, which page? Yes. So I mean, so Glashow wrote that SU2 cross U1 paper. Salam and Ward wrote that paper on marrying weak interaction with electromagnetism, but didn't talk about the mass generation. They said that it's a problem still. Well, I mean, as I said, I mean, group theory was very well explained by Kibble, and so then in 1967, Weinberg wrote the first paper having all the 3 things: how to marry weak interaction with electromagnetism, which is SU2 cross U1, and how to incorporate the idea of Higgs mechanism. I mean, the mechanism of mass generation, so that it was the first paper on what is called the standard model today, right? But Salam never wrote a paper. He gave a series of lectures. By that time, they realized, you see that they realized that it is going to be important. So Salam gave a series of talks attended by some people who later said that, so there is a preprint of those talks later on, not at that time. It was some kind of a set of lectures on SU2 cross U1 theory with the mass generation mechanism. So when it came to Nobel Prize eventually, okay, so so of course, I mean, Glashow, Salam, Weinberg, they got it because it's SU2 cross U1 theory for this thing. For the Higgs boson, of course, Higgs has to get it, right? Because it's only Higgs who talked about that radial excitation that will turn out to be the Higgs boson. But what about the others? The Brout died in 2011, 2012, it was discovered. So he's out, died 1 year before that. Angler, of course, Angler was included, but then it's a rule of 3. So then from Hagen, Kibble and Guralnik, you have to choose one that is impossible. So those two, maybe the third could have gone to Lee Evans, who constructed the LHC accelerator, but that was not given. Okay. So the mechanism of mass, but Higgs said that it's, I mean, Higgs did not, say that, well, although it was known as the Higgs boson, he used to feel embarrassed. He still feels embarrassed. He's still alive, right? Yeah. He's still, yeah. He's gone, no? I mean, this year, yeah. He used to feel embarrassed that, I mean, why it is called the Higgs boson, but anyway, and so much money has been spent for that I don't know, 10,000, 10 billion euro and so on. So essentially the mechanism, the mass generation mechanism is, you can call it, I wrote it somewhere. You can say, yeah, so this is the mass generation mechanism. Anderson, Brout, Angler, Guralnik, Hagen, Higgs, Kibble, and 't Hooft. Now, let me tell you what 't Hooft did. 't Hooft, see, it was not yet proved that this SU2 cross U1 theory is sustainable at all energy scales. It has to be what is called renormalizable theory. Okay. Now, so Salam had the idea that somehow electromagnetism and gravity put together will make weak interaction and strong interaction together. It will be renormalizable. It was a vague idea. Never wrote a paper on that. T.D. Lee also wrote a paper bringing in some hypothetical particles, how to make it renormalizable. But 't Hooft went to Karzay's summer school. Well, I'm advocating for many years summer schools because you may meet future Nobel laureates, you may get Nobel Prize for that as well. So 't Hooft, and then Lee was giving a set of lectures on pion physics. See, why a pion scattering, you know about this Frossa bound, I mean, the cross section has to saturate somehow, right? So pions are very similar to the formula I have written. No, the exponential, there are pions, which are the Goldstone bosons, and the sigmas are what I wrote sigma in the radial excitation, called Higgs. So when you consider pion pi scattering, I mean, he had the idea that it has to be mediated. No, sorry. Ben Lee gave a talk. Ben Lee gave a set of lectures that it becomes, it's not renormalizable, of course, but it becomes a, I mean, kind of tractable theory. Even at high energy, the cross section saturates, only that it doesn't have any abnormal growth. Only if you consider this pi mediated by sigma and then to pi scattering. So pi scattering mediated by sigma. So then 't Hooft got the idea that for WW scattering, when you consider WW scattering, the cross section, it has a 4W vertex that has a E4 kind of divergence, energy to the fourth. But then it gets cancelled if you consider other diagrams mediated by other WWZ and so on. But it still has the E square divergence. Okay. So only if you consider the intermediate radial excitation, which is this unwanted object that Higgs was forced to put because of referee's insistence, if you put that as an intermediate mediator, he had that idea that maybe it is the clue, like the sigma field in pion physics. So he came back And he told his supervisor, Tini Weltman, that I'll try this. But they needed some kind of a computer program, and Weltman wrote Spoonseek. That was one of the first computer programs on particle physics. So that had to be run at CERN only. So he flew to CERN, run that program, and then there was a factor of 4 missing, and this way that symmetry factor, they settled it, and then, oh, yes, my theory is renormalizable. The proof is much more complicated, because Etoft, early 71 or 72, he wrote his paper based on path integral formalism. Nobody knew path integral at that, although Feynman developed it. So formalism, nobody used it in particle physics at that time. So in 1972, there was a Rochester conference in Amsterdam. So in the backdrop of that conference, Weltman organized some kind of a parallel session, gave 1 hour to settle this issue. He wanted to launch Etoft, but Etoft means, although also he was a co-author at the same time of that paper, and he invited T.D. Lee, Sidney Coleman, and Salam to that room to, and Salam gave a lecture, which, I mean, kind of, it was known that it's clumsy. T.D. Lee gave his own idea about normalizability that also had to incorporate many things. Weinberg was also there. And then Etoft, who was a PhD student at that time, gave his lecture. Okay. Nobody understood because it was in path integral. But these people had this feeling that it is really important. Yes, 5 minutes. Yes, yeah. So it turned out that because of Etoft's paper, standard model got the respect that it deserved eventually. In fact, neither Salam nor Weinberg, after 1967, wrote a paper on SU2 cross U1 theory for the next 4 or 5 years. They moved to strong interaction. They didn't realize that this paper is going to be important. Only after Etoft's paper, they came back and started working vociferously on it. So again, in 2012, that's what Indu mentioned, when the Higgs boson was discovered, it was found to decay into 2 photons among many channels that, who mentioned it? I mean, you mentioned it, Kajuridi mentioned about the branching ratio. But the fact that, see, experimentalists don't care about your theory. So the fact that it is decaying into 2 photons implies that it has a spin 0 object. I mean, because a spin 1 object cannot decay into 2, a massive spin 1 object cannot decay into 2 massless spin 1 objects, Young's theorem. This is angular momentum conservation. So the spin 0 nature of the discovered particle was established at that time. Then from the angular momentum conservation, well, I mean, study of angular momentum and other things also established it's a spin 0 object. The parity was, kind of established. Well, I mean, there is still some room of that it is pseudo-scalar, experimentally speaking, but the chances are very small. It is a scalar particle. And this is the first time that if it is an elementary object, most likely it is, although the scope that, it's a composite object is still there, but it's more likely to be elementary than composite. So the first time you are seeing the Yukawa force, which is not quantized. Previously, you have seen gauge force, which is quantized and so on. So you can see that this is Higgs 2012, Honglayer and Rolf Feuer, the CERN Director General, celebrating. And this is the pic when Joe in Candela, right? I mean, that was the CMS spokesperson. I mean, showed it, our heart stopped. I mean, that is the Higgs boson. People have been looking for it. And you can see he mentioned at that time that so much money has been spent on it, feel embarrassed. Okay, so then, well, I mean, let me tell you, I mean, that the story, the standard model particle content, whatever was proposed is now discovered, okay? But as Rick mentioned that, I mean, we are still perplexed why the Higgs is light, in spite of the fact is more than 100 times heavier than the proton, but still it doesn't have any intrinsic sense of direction. It doesn't have a spin, it doesn't have any angular. So for a point particle which has no intrinsic sense of direction, again, as I said, I mean, it can eat up infinite amount of energy by eating its own tail in a various kinds of loops, and the mass will, energy is mass, so mass will shoot up to infinity, but it is 100 GeV. Why it is not So that thing is still an open domain. And one of the things that, you know, I mean, 10, 15 years back, in each such conference, 95% of the talks used to be on supersymmetry. Now, these days, only 5% talks are in supersymmetry. You know, the rating has fallen. The share market on supersymmetry is, but it turned actually supersymmetry is a very you know, elegant and mathematically consistent theory. I mean, so people thought that it would, still many people think that the symmetry is there, but it's broken in such a way that it is just beyond the boundary of our, you know, of our access through the accelerators. So people think about additional dimensions, like you know, it's curled so that a pencil, for example, I mean, you will see it as a line. So this from a distance. So if you come closer, means if you go to higher energy, you can unravel that higher dimension. Or supersymmetry is also kind of a higher dimension. I mean, you can think of, you know, you go to your imaginary dimension. Okay, so in the sense that, I mean, in real world, you don't, so you think that you are in some kind of this 3+1 dimension plus some imaginary dimension, which may be a fifth dimension, fourth, fifth, sixth dimension, or some kind of supersymmetry, which is also a fermionic direction. Okay, this is also extra dimension. Okay, so that can give you a solution to why the Higgs mass is 100 GeV. Let me tell you, I mean, why I call supersymmetry to be an additional dimension. It's a symmetry between fermions and bosons. It means that for every fermion there is a boson and vice versa. But you can think it in this way, that think of taking a square root of something impossible. Well, I mean, some impossible square root, like square root of -1. Okay, so 400 years back, somebody took the square root of -1 and said that this is the imaginary thing, right? This is a square, is something impossible, apparently. I mean, conceptually, square root of -1. But it opened up a new dimension, right? I mean, you can put your plot in the real axis and the imaginary axis. So taking square root of -1 gave you an additional dimension to sort of you know, I mean, represent your thought process. So if you take the square root of translation, for example, translation, like translation, rotation, these are the operators. So if you take the square root of translation, you get an additional dimension, which is the fermionic direction. And supersymmetry, superspace, the additional, when I'm talking about additional dimension, it is that direction that is going to give you supersymmetry, square root of translation. Okay, but how do you represent it? Like when you represent the imaginary axis, you still represent through real number 1, 2, 3, 4, 5, and in the imaginary a plus ib kind of thing. But if you try to represent things in super space, you cannot use real numbers, like, well, by real I don't mean the real and imaginary sense. The numbers that you know, 1, 2, 3, 4, 5, the way we know 1 cow, 2 cars, I mean, it's not those numbers. Okay, for angular momentum, yes, 5 times this, 4 times that. For spin also 3/2, 1/2, whatever. But for super space, you need to invoke certain numbers which are called Grassmann numbers. Okay, so let me give you an example. Like take a number a. Okay, a can be anything, a, such that a square is 0. Right, it's basically, you know, related to fermions. So 2 fermions, so square of a is 0, right? So take b square is also 0. Okay. Now suppose if they are ordinary numbers, a times b is b times a, right? 1 times 2 is 2 times 1, and so on. That is how we conceive the numbers. But if a square is 0 and b square is 0, and suppose addition works in the same way, like c is a plus b, then c square is also 0. C is also like, so then a plus b square is 0. So then a plus b square is a plus b times a plus b. So a square is 0, b square is 0. So then ab plus ba is 0. Agreed? So ab is minus ba. So these numbers, I gave you a very crude example. Okay, but these numbers which do not commute but anti-commute, are Grassmann number. Their square is also 0. So with that, you can describe the a full symmetry, where in addition to the standard translation, rotation, you can also include some symmetry in that, in those spaces and in the mixed spaces as well. And then you will see that for every spin half particle, there is a partner which is spin 1 and so on, and vice versa. Spin 0 has a spin half partner and so on. So that's a full, symmetry of particle and superparticles. But the symmetry is not there in nature. It is broken. Not only it is broken, it is very badly broken. So that is the reason we have not seen it. That is the way, but we expected to see it. But yes, 2 minutes and I'm done. -2 minutes, yes. Okay, so and another thing, I assume that Higgs to be an elementary object, but it can be composed. There are many other things which can be different types of new physics that Rick had mentioned and Kajuri had constrained. So with that note, I end, but I thought that I give you some kind of it was a storytelling about how the last 100 years work finally yielded something which relied on the previous decades, always, all the way back to 1920, 1930s. Nothing is unrelated. Okay, thank you very much.
Yeah, thanks, Gautam, for a very interesting talk. Are there any comments, questions? Yeah, just a moment.
Just a small thing with an error. Here is an error.
Oh,
It's an uncertainty. It's we don't call it error, that uncertainty of
uncertain.
about
Yes, yes.
100 MeV,
Okay, okay.
order of magnitude
Okay.
lower than
I
what
didn't change my slide for a long time. Now it is 100.
currently 110.
Okay, good. For the Higgs, most likely it is the most precisely measured fundamental object. Is it correct?
MZ.
No, MZ is 2 MeV.
92 G.
No, MZ uncertainty is 2 MeV. 2 MeV. No, 2 MeV. Okay. Anyway, so that's the most precise. Okay, but it's better than the top quart that nobody thought that Higgs would be measured to this even after Higgs was discovered. Forget about before. Even after Higgs was discovered, I must say one thing, that some of Ravindran's work turned out to be very important for the cross-section calculation. I should have mentioned, not only the former director Sudarshan's work was relevant for my talk, Ravi's paper is also relevant, was very useful for the experimentalist. So you have to be a mad science director. In order to be a mad science director, you have to be a very important person.
Okay. Okay,
Okay.
yeah, Srihari.
Just a quick question about
Yes.
the Higgs, Guralnik, Engler, all of those things.
Yes.
Which were the papers on U1 and who did that for non-abelian?
Sorry?
Which
Yeah,
was on the papers for U1
okay.
and
So the first was Engler and Braut. It was an U1. Just photon, how photon becomes massive. Okay. Then Higgs was on U1, but of course there is this additional twist of the radial excitation, which is the Higgs boson. And then the Guralnik Hagen cable again on U1. Okay. So then okay, prior to that, Glasson in 1962, means 4 years prior to them, he had this SU2 cross U1 paper, but no explanation of how they become massive. I mean, WZ become massive. Salam and Ward had a similar paper. So who married these two things, like mass generation with the Higgs mechanism? So that was 1967 Weinberg paper. So yes. Kibble was together with Hagen and Guralnik.
non-abelian, the Higgs mechanism itself.
Yeah, the Higgs, but it's not enough to do SU2. You have to do SU2 cross U1 and you have to have the angle and so on. So that Kibble didn't do. That I don't recollect. I mean, it was Higgs, Guralnik, sorry, Hagen, Guralnik and Kibble.
Kibble came to IMSC and gave a
Yes,
talk. I
yes, yes,
remember.
yeah.
He grew up in MCC. If there are any MCC students. Okay, so I don't see any other hands. So let's thank Gautam again. Hi. Thank the audience for patiently listening for so long to a very interesting talk. Thank you, Gautam.